Okay, in the first video we saw that some systems of linear equations have a unique solution, some have no solution, and some have an infinite number of solutions. So let's see if we can describe the solution set for different systems of linear equations. Okay, so for example, we've seen that this system has infinitely many solutions. If you remember, we showed that after you take this equation, this system of equations, and you apply this set of operations, followed by this set of operations, you get a system of equations like this. You get the trivial 0 equals 0 equation here, and in this case we have two equations and three unknowns. As I mentioned before, for any value of z, I can find solutions for these two equations. So let's try to describe the solution set. Let's use the second row to express y in terms of z. That means I leave y by itself on the left-hand side and move the z over to the right-hand side. Okay. Now, let's substitute that into the first row. That gets rid of the y from the first row. Notice that instead of y, I've replaced it with this expression. I can now solve for x by moving the z and constants to the right-hand side, and I get an expression like this, x equals 3 minus z. So y and x are both expressed in terms of z. Z can be anything. So we have our general solution. All right. So in our final solution, we can say z is a free variable. In this case, z is not a leading variable. So that's why I could let z be anything I want. So z can take any value. Z is free. Okay. A variable that we use to describe a family of solutions is a parameter. Okay, so it's convenient to use free variables as parameters to describe the set of solutions for a system of linear equations. And that's the standard way of doing things. You express all the other non-free variables in terms of free variables. So that means the free variables are the parameters in your final solution. Okay. Let's do another example. Okay, so here we have a system of three equations with four unknowns. You can follow through the arithmetic here and work it down to this final form here. Notice that here I have x is the first variable here, z is the first variable here, w is the first variable here, y is not a leading variable. The y is going to be my free variable. Okay, so let's see how that works. Okay. All right, the bottom row gives w equals 3. That's a necessary condition. Okay. Then the next row gives z equals 2. The top row is given, I can replace w and z into the top equation. And that gives me an equation just with x and y. If I solve for x, I get x equals 1 minus y. Okay. All right, here's another example. This equation system is already in echelon forms. So in this case, y and w are free variables because the x and the z are leading variables. So we can make y and z arbitrary. Let's do the same thing that we've always been doing as you solve from the bottom up. The first equation down here, I'm going to solve for the leading variable z in terms of w. Then when I work my way up from that, I'll substitute the value of z in to the first equation. I still have three variables, x, y, and w. I want to solve for the leading variable x, and I get this result as for x in terms of y and w. So notice that I have both z and x in terms of y and w. I've parameterized my set of solutions in terms of the free variables y and w. Okay, we've been working with equations, and it takes a lot of writing to write all of these variables, and a matrix gives a way of writing the same information in a much more compact form. Okay? A matrix is a rectangular array of numbers with m rows and n columns. And each number in the matrix is called an entry, so we'll see some examples here. This is a 2 by 3 matrix. 2 is the number of rows, 3 is the number of columns. 2 rows, 3 columns. In this case, m equals 2, n equals 3. Okay, if I want the entry in row 2 and column 1, typically we use the lowercase letter to denote individual entries, and we use an uppercase letter to denote the matrix. So B21, that means second row, first column. You always do it this way. The first index on your entry is always the row index. The second index is always the column index. That's the universal convention. So to find this entry, row 2, I go down 2, and this 1, that's the column, so I go over 1, that gives me a 4. Okay, so that's why B21 equals 4. In exercise, you can ask yourself, what is B23? All right, B23 is going to be 6. What is B32? Well, there is no B32, okay, because there aren't 3 rows. Let's continue here. All right, a special case of a matrix is called a vector. Now, we typically use column vectors as our standard for vectors. So a vector is a matrix with a single column. Okay, a matrix with a single row is a row vector. The entries of a vector are its components. And a column or row vector whose components are all 0 is a 0 vector. Right? These are straightforward definitions. Okay, so here's some example. Here we're going to use vector with over arrow, and many authors use boldface. In my own handouts, I use boldface. So the two notations are just as good as each other. All right, here we have a vector or column vector with 3 components, and he denotes by V with an arrow over it. Okay. Here we have a row vector with 3 components, and here we have a 2-component 0 vector. Now we can think of this row vector as living in 3-dimensional space. We can also think of the column vector with 3 components as living in 3-dimensional space. This column vector with 2 entries we can think of as living in 2-dimensional space. Okay, we can do algebra with vectors. I'm sure in high school you saw vector addition. You represent vectors as arrows and you sum head to tail. We can do the same thing algebraically by taking the 2 vectors. The first vector is represented by its components. This is an n-dimensional row vector. I need to, if I want to add to another vector, the other vector also has to be n-dimensional. The 2 vectors must be the same dimension. And if one's a column vector, the other must be a column vector. And I add them in the logical way as adding the different components together. This is actually the very same thing as vector addition, where you sum vector arrows head to tail. You can work that out and see that that's true. Of course, it's hard to draw arrows in n dimensions. You can only do that in 2 dimensions and maybe in 3 if you're very creative. But the principle is the same for n dimensions. Okay? So this is the sum of 2 vectors. The scalar multiple of a vector, well, I just take every component of the vector and multiply it by r. That's kind of like scaling up the vector. That's a good reason for calling it scalar multiplication. If I have a vector that I could represent by an arrow, oh, that's a terrible straight line. If I have a vector that represent by an arrow like this, okay. If I want to scale it up, suppose my r was 2. Well, r would multiply each one of the entries of this vector by 2. This here would be the origin. Sorry, I didn't take my pen. Okay, so here's the origin. Here, let's do that again. The origin is this point here. And here's my vector v. Okay, if I want to scale up the vector v by a factor of 2, well, I just go in the same direction and I go out twice as far. Sorry for the bad lineup, but you can get the picture. This vector is twice as long as this one, and it's in the same direction. This would be 2v. All right, so that's scalar multiplication, scales the vector. Now I can do a combination of these 2 operations. I can scale vectors and add them, and you get this kind of algebraic equation. And you can verify that this equation is true. Okay? All right, now instead of writing all the variables out when we write a system of equations, we can simply write the matrix of coefficients. So notice we have here the matrix of coefficients, and then there's a vertical line, and then you have the vector of constants. Okay, and we can keep track of the variables simply by keeping the coefficients in line. Okay, so rather than writing x, y, and z, we just keep the coefficients in line. In this particular case, if I wanted to eliminate the x from the second equation, you can see what I'd have to do is I'd have to add 1/3 times the first row to the second row. That's expressed by this operation here. Similarly, if I wanted to eliminate the x from the third equation here, I'd have to take the first row and subtract 1/3 times the first row. That's expressed by this operation here. We can do this in shorthand using matrix notation and get this result, and continue to do these Gaussian row operations using only the matrix of coefficients. This is called the augmented matrix because you have this matrix of coefficients, which is augmented by a column vector of constants. Okay. Once we've gotten down to this point, you can see that we have 2 leading variables, 1 free variable, and we can go ahead and solve in our usual way. Okay. So here's the usual solution. Okay. We could write the solution set in vector notation. Notice that when we did find the solution, we got y and x in terms of z. If we write x, y, and z as components of a 3-dimensional vector, notice that x is 1/3 plus 2/3 times z. We can treat this z as a scalar multiple. Okay, so I put the 1/3 in this vector and the 2/3 in this vector, and this vector over here is going to multiply by z. For the y, I have 1 plus 4/3 z, so the constant, component in the constant vector is 1. The component in the vector scaled by z is 4/3, so that's where the 1 and the 4/3 come from here. In the last one, well, z equals z, and we get this vector equation. So you should verify and make sure you understand why this vector equation is the same as this system of 2 equations here. Okay. All right, so let's do another example. Here we have 4 variables in 2 equations. We're only going to be able to eliminate 1 variable, so we do so here. We get this reduced system. This is in row echelon form. Okay. Now, what are our free variables? Well, our 2 free variables are this one and our, let's see what we said, this is w and z are our 2 free variables. Okay. And notice that each one of these 3 free variables we treat as a scalar to multiply a vector. All right. You can go through and figure out what this system of equations is going to mean. This is the same thing as, I could write this out. I could write this as minus 5 y. This is actually plus w equals 1, so I could write this as equal to 1 minus w. Okay, and the equation up here is going to give me x plus 2y minus z equals 2. All right, now I want to express x in terms of the other variables, so that's going to give me x is equal to 2 plus z minus 2y. Okay, but let me go ahead and substitute for y in here. I could divide this by minus 5, and I'll get y equals 1 minus w over minus 5. Okay, if I substitute this y in for here, I'm going to get x is equal to 2 plus z minus 2, and let's substitute in for what I get for y, 1 minus w over minus 5. And if I do that simplification out, well, you can see that here I'm going to have a 2, and this 2 is going to be added to the constant part from this expression. Notice I have a minus 2 here and a minus 5 here, so that becomes plus 2/5. 10/5 plus 2/5 is 12/5. So it's going to give me 12/5. Okay. And then let's see what the z is multiplied by 1. So I'm going to get plus z. And then here for the w term, I have minus 2 over minus 5, which gives me 2/5. But I get a minus, another minus, so that's going to be minus 2/5 w. Okay? So here I have an expression for x. X equals 12/5 plus z minus 2/5 w. All right? If I want to write that as a vector, I'm going to have my x, y, z, w, and each corresponding entry of each vector is going to express one equation. Notice the equation I have here. X equals 12/5 plus z minus 2/5 w. Do you see how that corresponds to here? My solution I can think of as x, y, z, w. Here's my 12/5, and here is my 1 times z, which corresponds to this term. And here I have minus 2/5 times w, which corresponds to this term. Okay? Where does this second equation come from? Here I have y equals minus 1/5 plus 0z plus 1/5 w. If you work out this equation here, that's exactly what you get. Y equals minus 1/5 plus w over 5. That's expressed by this second equation here. Right. The third equation just expresses z equals z, and the fourth equation expresses w equals w. So I've written the solution set for this system of equations in a very compact way. And here, notice that when I wrote the solutions here, I didn't even write the variables x, y, z, w. That's because the component is a bookkeeper that tells me which variable goes where. Okay, so very compact way of writing the solution.